If Earth doubled in size overnight, the first thing you'd notice when you woke up is that you couldn't get out of bed. Not just you, your dog, your cat, even the potted plants in your house would behave differently. The tree in your backyard would probably have collapsed, and if you looked out the window, the horizon would appear farther away than ever before. So would your house's yard actually get bigger too? What would happen to gravity? How would the atmosphere change? Could trees remain standing? Could airplanes still fly? And most importantly, how would you survive? Tonight, we'll answer all of these questions, and some answers are stranger than you might imagine. But first, let's understand what's actually happening. Earth's diameter is currently about 12,742 kilometers. If this doubled overnight to 25,484 kilometers, it's not just a size change. If Earth's density, the amount of mass in a unit of volume, stays the same, a much bigger change occurs. Volume is proportional to the cube of the radius. To simplify the math, when Earth's radius doubles, its volume increases eightfold. And if density remains constant, mass also increases eightfold. Now gravity comes into play. Isaac Newton's law of universal gravitation from the 1600s states, "Every mass attracts other masses." This gravitational force depends on two things: the size of the mass and the distance. The formula goes like this: gravitational force is directly proportional to mass and inversely proportional to the square of distance. Earth's mass increases by 8 times, but the radius, the distance from center to surface, doubles. The square of distance equals 4. When you divide 8 by 4, you get 2. So surface gravity exactly doubles. What does this mean? Everything's weight doubles. But it's not just the number you see on a scale. It's the actual weight your body feels. Because weight is actually the force of gravity pulling you down, your mass stays the same. You're still made of the same amount of bone, muscle, and water molecules. But Earth is pulling you with twice the force. And this simple physical change affects everything, from how you move your body, to how trees grow, to how the atmosphere behaves. Now let's see what this actually means in reality. Let's start with the simplest question. Does your house's yard get bigger too? Actually, yes, but not how you think. Your house itself stays the same size. The bricks, rooms, garden fence, all remain unchanged. Because they're not part of Earth, they're objects sitting on top of Earth. But Earth's surface expands, so the distance between your house and your neighbors doubles. The distance from your house to school doubles. Everything becomes farther away. Now for the more interesting part, you. If you stepped on a scale in the morning, normally weighing 50 kilograms, you'd now see 100 kilograms. But this isn't just a number. Your body will actually feel that heavy. Going downstairs, normally easy, now it feels like you're carrying someone on your back. Lifting your school bag, twice as hard. Running, nearly impossible. Think about playing basketball. Throwing the ball in the air requires twice the force. Jumping? If you normally jump 50 centimeters, now you can barely manage 25 centimeters. Dunking becomes a dream. Or consider soccer. The ball weighs the same, but you're twice as heavy. Running is exhausting. A 90-minute match? You might collapse exhausted in 30 minutes. But the strangest part happens with animals. Your dog tries to get out of bed, but its legs tremble. Large dog breeds, golden retrievers, German shepherds, really struggle. But small dogs, like Chihuahuas or Yorkshire Terriers, move almost normally. Why? Because gravity's effect isn't proportional to size. For small animals, double gravity is still manageable, but for large animals, it's catastrophic. Watch the birds in your garden. Sparrows can still fly, but with difficulty, flapping their wings faster. But large birds, crows, pigeons, have completely given up flying and now walk on the ground. And trees, that tree in your yard, it probably collapsed on the first day. Its trunk couldn't support its own weight. Large branches broke. Only short, thick trees remained standing. But the most surprising part, ants. Look at the ant nest in your garden. Ants are working normally, as if nothing changed. Carrying food, building nests, everything normal. Because for ants, gravity isn't a huge factor to begin with. They're so small that even double gravity doesn't affect them much. Actually, this new world might be ideal for insects. Now think about taking a shower. You turn on the faucet and water flows, but differently. Droplets fall faster because gravity is twice as strong. Water rushes down to the ground the moment it leaves the pipe. Now your body, what's it doing? The first hours are very difficult. Your heart beats normally, but blood circulation has become harder. Blood pools in your legs. You feel a bit dizzy. The best position is lying down. In a horizontal position in bed, the heart does its job more easily. When you stand up, you can't stay upright for long. Sitting is better. As days pass, your body begins to adapt. Your legs swell. This is your body's attempt to balance the pressure. Your muscles ache because they're constantly working. But interestingly, after a few weeks, you start to notice something. Walking becomes slightly easier. Your leg muscles have developed. Your endurance has increased. After 3 months, you've almost adjusted. Still exhausting, but much more manageable. Your body has adapted. Bones are particularly interesting. Under stress, bone tissue becomes denser. Your leg bones, spine, skull, all gradually thicken and strengthen over time. Even your heart grows larger. Because it needs to work harder, the heart muscle develops, just like how athletes have larger hearts. And babies being born, they see this world as normal. For them, this is the only reality. They're born with stronger bones and larger hearts. Evolution has accelerated. Why did trees collapse? Because trees' growth limit is determined by gravity. As a tree grows, it must transport water from its roots to the leaves at the top. This means working against gravity. The taller the tree, the more energy required. The tree produces energy through photosynthesis. If the energy it produces exceeds the cost of water transport, it continues to grow. But at some point, cost exceeds gain. On normal Earth, this limit is about 120 to 130 meters. California redwoods approach this limit. With double gravity, this limit is cut in half, so maximum 60 to 70 meters. Current giant trees are far above this limit. For them, remaining standing is impossible. But nature adapts quickly. New shoots emerge, growing differently, shorter, wider, with branches closer to the ground. 20 years later, new forests form, but they're unlike old forests. No tree is taller than 20 meters. Most are 10 to 15 meters. Now look outside your window at night. The moon is still there, but appears slightly different, perhaps brighter, and each night slightly larger. Because Earth's gravitational pull has increased, pulling the moon more strongly. Slowly, the moon is approaching us. In the first year, the difference is hard to see. But 5 years later, the moon is noticeably larger. 10 years later, the night sky is very bright. During a full moon, the moon occupies a large portion of the sky. There's a limit to how close the moon can approach, called the Roche limit. This is the closest distance the moon can approach Earth without being torn apart by tidal forces. Thousands of years later, the moon gets so close it begins to break apart. Cracks form first, then large pieces break off, and finally, the moon disintegrates. A ring forms in the sky, just like Saturn. Night is never completely dark anymore. The ring reflects sunlight in perpetual twilight. The air feels different. Take a deep breath, denser, fuller somehow, because the atmosphere is more compressed. With each breath, you're taking in more oxygen molecules. The atmosphere is held by Earth's gravity. Under normal conditions, light gases, hydrogen, helium, gradually escape to space. But heavy gases, oxygen, nitrogen, are held by gravity. With double gravity, the atmosphere is held much more tightly. The same amount of air is gathered more compactly close to the planet's surface. This increases pressure at sea level. Normal atmospheric pressure is around 1 bar. With double gravity, it might approach 1.5 to 2 bars. You feel slight pressure in your ears, like on an airplane, but constantly. Within a few weeks, you adjust. The good part, breathing becomes slightly easier. Even at high altitudes, there's sufficient oxygen. And sounds, they sound different, fuller, deeper. Even your own voice comes out lower. Everyone sounds a bit like Barry White. The sky is different too, deeper blue. Sunsets more dramatic, more colorful, because light passes through thicker atmosphere. Airplanes no longer fly. Within the first month, all flights were suspended because flying requires twice the fuel. It's not economical. In fact, some planes can't even reach takeoff speed due to gravity. For a plane to fly, the lift force produced by its wings must exceed its weight. With double gravity, weight doubles, but lift force remains the same. So most planes can't even take off. But trains still work and are actually more popular. Everyone uses trains now. New rail lines are being built, connecting cities with high-speed trains. Buildings have changed. Skyscrapers are no longer being built. The tallest buildings are 3 or 4 stories. Cities expand horizontally, not vertically. Think about New York. Its old skyscrapers collapsed. The Empire State Building fell in the early years. Now, in its place, single-story structures stretch for kilometers. Underground cities are popular because underground, gravity-related problems are fewer. Some cities are entirely underground. Tokyo, Paris, London all have large underground sections. Some people have begun living underwater in specially designed submarine colonies. Because in water, you don't feel gravity. Life is easier. Large underwater cities have been built in the Pacific and Atlantic Oceans. Underwater domes house thousands of people. These sea people are beginning to evolve differently. Stronger lungs, more efficient oxygen use, bodies more resistant to pressure changes. Perhaps hundreds of years from now, they'll become a new human species, Homo aquaticus, the water human. Years pass and generations change. Your children are born into this world. For them, this is normal. They don't know the old world. The stories you tell seem like fairy tales to them. Grandma, could people really fly in the air? They ask. There were airplanes, you say, giant machines that flew in the sky. They find it hard to believe because to them, flying seems impossible. This new generation is different from you, shorter but much stronger. Thick legs, prominent muscles. A 10-year-old child is as strong as a 20-year-old from your youth. Natural selection is at work. Individuals with stronger bones and larger hearts survive more and have more children. The gene pool is changing. Average height is decreasing. 100 years later, average human height might be 1.40 to 1.50 meters. Because a shorter body requires less energy and is more stable. Let's talk about something fascinating: how evolution works on different scales. For insects, the square-cube law works in their favor. As an object's size increases, its volume, and therefore mass, increases by the cube of the scaling factor. But its cross-sectional area, which determines structural strength, only increases by the square. This is why ants can carry many times their own body weight. Their muscle cross-section is large relative to their body mass. For large animals, this relationship works against them. An elephant's legs must be proportionally much thicker than a mouse's to support its weight. With double gravity, this problem is magnified. Large land mammals would need impossibly thick legs. So evolution favors smaller sizes. Swimming is interesting because water provides buoyancy through Archimedes' principle. An object submerged in water experiences an upward force equal to the weight of the water it displaces. Since the human body's density is close to water's, we're nearly weightless when submerged. Even with double gravity, water still supports us. That's why aquatic life continues largely unchanged. Bone density changes are particularly interesting. Bones remodel constantly through a process called Wolff's Law. Bone tissue responds to stress by becoming denser and stronger. This is why astronauts in zero gravity lose bone density. There's no stress. In double gravity, the opposite happens. Constant increased stress causes bones to become remarkably dense. After several generations, human skeletons might be 50 to 70% denser than today. The cardiovascular system also undergoes significant changes. Blood pressure increases because gravity pulls blood downward more strongly. To compensate, blood vessels develop thicker, more elastic walls. The heart must work harder, so it enlarges. But there's a limit. Extremely large hearts become inefficient. Evolution finds a balance between heart size and body size. Perhaps future humans will have hearts 40 to 50% larger by volume, but more efficient. Earth's interior is more dynamic than it appears from outside. When planetary mass increases, the amount of radioactive elements inside also increases. Elements like uranium, thorium, and potassium naturally decay while producing heat. This heat keeps Earth's core and mantle hot. More mass means more radioactive elements, and therefore more heat. This increases geothermal activity. Volcanic activity would likely intensify. Magma exerts more pressure on the crust, finding exit through weak points, volcanoes. New volcanoes might form, and existing ones become more active. Tectonic plates are sections of Earth's crust in constant motion, pushed by convection currents in the mantle. More heat means stronger convection currents, potentially accelerating tectonic movement. If plates move faster, earthquakes and mountain formation occur more frequently. Rapid changes occur on geological timescales, but in the long term, a new equilibrium forms. The system settles into a new balance point between heat production and heat loss. The atmosphere's behavior becomes more complex with increased gravity. Weather patterns change because a larger planet has more surface area and therefore more climate diversity. New oceans, new continents, new mountain ranges, each affects local climate systems. Wind patterns shift as denser air carries more momentum. Storms might be less intense, but longer lasting. The Coriolis effect, caused by Earth's rotation, also changes. On a larger planet, rotational velocity at the surface is higher if rotation period stays the same. This affects how hurricanes and cyclones form. They might become larger, but rotate differently. Physical changes lead to psychological and cultural changes too. Constantly expending more energy affects people's general energy levels. Fatigue becomes more common. This can reduce social interactions as people conserve energy by becoming more introverted. But conversely, hardships can bring society together. Common struggle encourages cooperation. Perhaps societies become more collective, more solidarity-focused. Art and culture reflect these changes too. Music perhaps becomes slower-paced, more meditative. Dance involves movements close to the ground rather than leaping upward. Visual arts prefer horizontal compositions. Value systems change. Physical strength becomes more valuable. But at the same time, energy efficiency and sustainability become central values. Religion and philosophy are also affected. Perhaps new mythologies develop. Cosmic events like the Great Heavying enter religious texts. Gods become associated with gravity and mass. Education systems transform completely. Physical education classes are entirely different. No more running, replaced by balance, strength, and flexibility exercises. Even math classes change because gravity calculations have changed. The gravitational acceleration, formerly 9.8 meters per second squared, is now 19.6 meters per second squared. All physics problems have been rewritten. Schools themselves are designed differently. Single-story buildings with wide hallways. No stairs. Everything is on one level. Playgrounds are close to the ground with gentle slopes instead of tall slides. Recreation has fundamentally changed. Outdoor activities are limited because they're too exhausting. Indoor entertainment becomes dominant. Board games, video games, virtual reality. These don't require physical exertion. Virtual worlds become incredibly popular because there you can experience the freedom of the old Earth. In VR, you can jump high, run fast, even fly. These simulations become a form of nostalgia for a world that no longer exists. But all of this is just imagination. Right now, Earth is its normal size. You weigh your normal weight. Trees still reach toward the sky. Birds still soar in the heavens. Thinking about this scenario actually reminds us of something. How delicate a balance we're in. Earth's size, mass, distance from the sun, everything is exactly where it needs to be. If it were slightly different, life would be completely different, or perhaps wouldn't exist at all. There are other planets in the solar system. Jupiter is 11 times larger than Earth. There, gravity is much stronger. The human body couldn't survive even a second. You'd be crushed immediately. Mars is smaller than Earth, with a radius about half of Earth's. There, gravity is much weaker, 38% of Earth's. You can jump very high, but over time, your body weakens and your bones deteriorate. Venus is very similar to Earth in size, but its atmosphere is vastly different, 92 times denser, with temperatures of 450 degrees. life is impossible. But Earth is exactly the right size. In the Goldilocks zone, it's not just distance from the sun that matters, but size too. And we are the fortunate beings living in these perfect conditions. There are trillions of planets in the universe, but as far as we know, a planet like Earth is very rare. Exactly the right size, exactly the right distance, exactly the right atmosphere. Perhaps billions of years from now, Earth will change. As the sun grows, Earth will heat up and oceans will evaporate. But that's a very distant future, about 5 billion years away. For now, this blue planet is our home. In this perfect balance, we live, we breathe, we exist. How fortunate we are. The universe is a vast laboratory of possibilities. Different gravitational constants, different planetary masses, different atmospheric compositions. Each combination creates entirely different worlds, some too hot for life, some too cold, some with crushing gravity, some with almost none. But here, on this particular planet, in this particular solar system, in this particular galaxy, conditions aligned perfectly. Not by design, but by the mathematics of physics and the randomness of cosmic evolution. And in this brief moment of cosmic time, we get to witness it, to understand it, to question it, to imagine alternatives. That itself is remarkable.